Okay. Now we got x, y, and z. Here's your xy plane. So if we've got a point, let's say here. Now where is that point? Well, let's project it down into the xy plane. So now we can see where it is. It's out along this direction from the origin in the xy plane, and then it's up this high. So this is a point x, y, z. Well, then what are the coordinates of this point? Now you don't really have to copy this picture down, but of course if that helps you focus on what's going on, okay. But you're going to see this picture in your book. If you Google cylindrical coordinates, you're going to see this picture, okay? So take a second and write down what you think the coordinates of this point are. Okay, got that instantly. I thought you would, but I just wanted to make sure it was, okay? So that's important. Okay, so here's x, y, 0. So here is the vector from the origin to x, y, 0. You're in the xy plane. So this coordinate is r. And this angle is theta. Is that easy to understand? I hope that's totally obvious. Okay? So, cylindrical coordinates are r theta z. So that's what r and theta are. Okay? So really all you got to do to move between cylindrical and rectangular coordinates is just what we do with polar coordinates. Okay? With the x and y, or with the r and theta. You know, and x equals r sine theta, cosine theta, and y is r sine theta. Just like polar coordinates. So all it is you project your point down into the xy plane and do polar coordinates there. Okay? And keep z. Okay? So that's easy. And you could then take an equation like x squared plus y squared plus z squared equals 25. What's that? What kind of quadratic surface is that? You can show me with your hands if you understand. You're going to make a gesture that looks kind of like this. It's a sphere. Because the distance from the origin to this point is 5, right? because the distance from the origin x, y, z is the square root of x squared plus y squared plus z squared. Okay? So, it's a sphere of radius 5. If you intersect it with any of the coordinate planes, you'll get x squared plus y squared equals 25. That's a circle of radius 5 in the xy plane. In the xz plane, y0, x squared plus z squared equals 25. That's a circle of radius 5 in the z plane. So you got circle of radius 5 here, circle of radius 5 here. And in the yz plane, this plane, you got it here. If you visualize those three circles, then you see that they're part of a sphere of radius 5. Then you could intersect this, say with the plane z equals 3. Then z squared would be 9. And x squared plus y squared would be 25 minus 9, which is 16. And so when z is 3, you got a circle of radius 4. Just slicing the circle. Higher and higher planes can't go up past z equals 5 because you get a negative here. And two squares can't add up to a negative, so you don't have any more points. And so you should understand that in terms of what you did. But of course, you only got introduced to quadratic surfaces 2 days ago, and it hasn't really quite seeped in. It needs to keep seeping, okay? But you got time to let it seep, because we won't really use them for quite a while. Okay? I want to review it every once in a while. Okay, well, there we have the sphere of radius 5. And we want to put this in cylindrical coordinates. Well, x is our cosine theta, y is our sine theta. Let me get the spherical. You get r cosine theta quantity squared plus r sine theta quantity squared plus z squared equals 25. Well, that's r squared cosine squared theta plus r squared sine squared theta plus z squared equals 25, which is r squared times cosine squared theta plus sine squared theta plus z squared equals 25. And what's that? Okay, take a look at the equation. Don't sit there writing. You got plenty of time to write. When I post these, you can copy them down with my artistic handwriting if you want to try. Okay. How does that simplify? If you did trigonometry right, you would instantly see that cosine squared theta plus sine squared theta is 1. That's the Pythagorean identity. Okay? So you're shaking your head, you know, that's familiar. Not as familiar as it ought to be. And it's not as familiar as it's going to be. Because it pops up all the time, which is why I use this example, okay? You always want to look for the Pythagorean identity when you're converting from one coordinate system to another, okay? So that's just r squared plus z squared equals 25. Now, why should that be? Look here. Here's the origin. Here's a line segment or a vector of length r. Here's a vector of length z, right? If I do this, I have a right triangle because the vertical line is perpendicular to any line in the xy plane, okay? Because the k vector is normal to the xy plane. You want to think about that terminology. It's going to get real important. Okay. So you have r here, you have z here. It's pretty obvious from this picture. That this is the square root of r squared plus z squared. Okay? Well, square root of r squared plus z squared is 5 for this equation. And a set of all points at distance 5 from the origin is the sphere of radius 5 centered at the origin, right? Okay? Now, if you wanted a sphere of radius 5 centered at some other point, well, you'd have a little work to do. You have to understand translation. Okay? And then, in that case, there's a little twist to it if you try to do R with translation, but leave that for another time. Okay? Now, you're going to have to do some digging on spherical coordinates. I really couldn't start talking about spherical coordinates until we did all this. And am I running out of board space? Not that time. And I might as well use it. Okay. So, spherical coordinates. In spherical coordinates, we use two angles. Okay? Now, in spherical coordinates, we've got a point here. We'll project it down into the plane. And we're going to get our usual cylindrical coordinates. R and theta. Okay? R is not a spherical coordinate. So I'm going to circle theta to say that's one of our spherical coordinates. There are three. You need three coordinates in whatever system to describe a point in three-dimensional space. That's why the space is three-dimensional. The whole concept of dimensions is a little more subtle than that, but that's sufficient for right now, okay? So, theta is one of our spherical coordinates. Now this point could be x, y, z, or r theta z. The other, well, it's the one distance coordinate you have in spherical coordinates is the distance from the origin to the point, which incidentally makes it really easy to write the equation of a sphere in spherical coordinates. That's why we call it spherical. Just like it's really easy to write the equation of a cylinder in cylindrical coordinates. Okay? You'll see that. I don't have time. I don't think I have time to do it. And it's so obvious and straightforward that I don't really need to prime you on that, okay? Normally I would. We have the whole hour to do this, but we don't. This coordinate it's not P. It's rho. Like this is simple arc, okay? No stem on it. And it's not straight, okay? And also, you don't want to mispronounce it. If you pronounce it P, it's something you don't want to do. Okay? Row your boat. That's how it's pronounced, okay? Don't call it P. So, there's your cylindrical coordinate. And finally, you need a third coordinate, because if you know rho and theta, then all you know is you're on a circle. Okay, if theta is constant, you have a plane, okay, down here, x, y, z. If theta is here, then every point with that theta has to lie on this plane. Any other point would project down to some point that isn't on the straight line through here, okay? again, you have to read about a lot of that. Okay. The third coordinate is phi. Some people pronounce it phi. My fraternity when I was in college was Phi Kappa Psi, not Phi Kappa Psi. Okay? Pronounce it phi, you get another unfortunate pronunciation, but that's phi. But a lot of mathematicians say phi. There are even some physicists who are silly enough to say phi. A lot of these people, most of these people know a whole lot more than I do, but they don't know how to pronounce this. Okay, well, there are two pronunciations. We're going to use phi. Okay? So, I don't know how the Greeks said it. They didn't have tape recorders back then. Okay? Much less video cameras. So now the polar coordinates are rho, theta, and phi. Rho equals x squared plus y squared plus z squared, which is also r squared plus z squared. Well, if you have the point in polar coordinates, that's how you get rho. If you have the point in cylindrical coordinates, this is how you get rho. Or in rectangular coordinates, wait a minute, I'm saying it wrong. If you have the point in cylindrical coordinates, this is how you find rho. If you know the point in rectangular coordinates, this is how you find rho. If you have an equation in polar coordinates, okay, then, well, I haven't written down what you need to use yet, so we'll save that. Theta the usual definition, right? And z. Sorry, phi. Going the wrong way. Phi is what? Where's a triangle a right triangle you could use to find phi? Yeah. You project back at a right angle to the z-axis, and you see that phi is, well, okay, this distance would be r which is the square root of x squared plus y squared, right? So phi is the, well, that's the opposite side, rho is the adjacent side, and z here is this side, okay? So phi is the inverse tangent of the opposite over the adjacent, right? So that would be r over z inverse tangent of square root of x squared plus y over z. Okay? I've got a problem with that. Maybe there's something wrong with with what I just wrote. Because of course, if z goes negative, you get the negative angle, and phi should be between 0 and 180 degrees. Now, look it up, there's something pretty obvious. But if you're down here below, you get a negative, and don't regard phi as a negative angle. So, tell me, you see something wrong with this? There's an angle. This is opposite, this is adjacent.
That would be the hypotenuse, wouldn't it?
No, rho's hypotenuse.
Yeah.
Okay, so I'm going to put a question mark here. I believe I messed that up, or maybe I did. Anyhow, it's simple. Look at the picture, you get it. And then you have conversions, okay? Like R is equal to what? It's equal to rho times the sine of theta, if you look at this triangle, okay? So, R equals rho sine theta. Now in cylindrical coordinates, theta is the same between the two coordinate systems, right? And then z is rho cosine theta. And I said theta. Anytime now I'm going to start calling that thing t. Phi. Okay? Again, that should be obvious from this triangle. And the fact that this is equal to r. Okay? So clearly, take hypotenuse times the sine, you get the opposite side. Take the hypotenuse times the cosine, you get the adjacent side, which is c. Okay? So spherical coordinates shares one coordinate with cylindrical, right? And cylindrical, as you saw, shares one coordinate, z, with rectangular. You notice that spherical doesn't share any coordinates with rectangular, right? The advantage of these systems is that some things like spheres are really easy to represent in spherical coordinates. Just rho equals whatever the radius is. There's a sphere through the origin, right? Cylindrical, if you say r equals 5, what do you got? You got all the points down here in the xy plane where r equals 5. That's a circle, radius 5 about the origin. And then all the points above and below that are still equal to 5 because you project the point down to the plane. That's a point you want to, people often get confused on. Okay, so in rectangular coordinates, it's easy to define rectangular parallelepipeds, rectangular solids, okay? X has constant bounds, Y has constant bounds, and Z has constant bounds, okay? It's really hard to do that in spherical coordinates, to do a rectangular shape in spherical coordinates, okay? Now, I just naturally, when I did this, worked out how to do it, okay? Because I had enough time that semester to do it, which is one reason I did pretty well in this course. But so if you want to be proactive, you think about things like that, whether you actually have time to do it. How would you do a box in spherical coordinates? It's a little easier in polar coordinates, but it's really easy in rectangular. So if you're talking about boxes, you're going to use rectangular coordinates. If you're talking about spheres, you probably want to use spherical coordinates. If you talk about cylinders, you probably want to use cylindrical coordinates, okay? Now it goes beyond that, you know, you do portions of cylinders and stuff like that. Again, we're out of time, so I can't talk about that. And the other set of equations is x equals what? Well, x would equal r cosine theta, right? But r is not a spherical coordinate. So if you've got the spherical coordinates, rho theta and phi, how are we going to get x? Well, we project the point down here, and we have this, right? And this is what? Well, that's just rho times the cosine of, that's times the sine of phi, okay? And then we've got theta, so we can do rho sine phi times the cosine of theta. I'll group this, it doesn't have to be grouped, but this is like r cosine theta. Similarly then, y is just cosine phi sine theta. And z, well, that's shared with cylindrical coordinates. It's the same. And because it's just, this triangle here tells you it's rho cosine phi. So you have here all the conversions between cylindrical and rectangular and spherical coordinates, okay? And that's really what the section is about. Now, unfortunately, we don't have time to talk about the other assignment that's going to be due. So I'm going to make myself a note right now to do a video. It's on space curves. So, 5 to 10. I should have time this afternoon to do a video. Space curves. That's where you're going to need the parametric equations again. Okay? Pretty easy.